me get the other computer so I can see the stream. Jack, I hope you're doing well this morning. So the brilliant idea I had, let me know what you guys think, is how would a sort of studio slash coding day of class work? Where, does that sound like it would be kind of useful for us to just sit around and hammer through some code and you guys work through things and I kind of float around and help you guys out? Huh? Yeah, okay. That's the question, right? The logistics of it. So, um, the idea I had was uh, maybe the Ed Tech Center in the library because it has a bunch of PCs with monitors, so we could just plug the Pis into the monitors and then probably also the mice and keyboards there or something. So right after class, I'm going to go over there and talk with Aaron Elam, who runs the show, and see if that would be doable. Um, yeah, uh, so I'll see what I can work out for next week, um, sometime either Tuesday or Thursday. We'll see. Um, okay, so let's see. Twitch moderator, Prof. McKinney. Um, anyway, and it looks like audio. I don't want to hear my stupid voice. Um, okay, so let's get to it. So the first thing I wanted to talk about was actually the issue uh, that I ran into talking with Jack yesterday about. He was working on the triangular numbers with scanf, right? So that addition to the routine. So let's open up one thing here and let me demonstrate the issue. Um, okay, so the first thing is we didn't notice the issue with the sample or the program we were writing last time because the program we were writing last time took in a string, meaning a sequence of characters, not a number. Okay. So let's just write a new program to kind of demonstrate what he ran into. Okay. Um, oops. Let me actually make a new project. New. We'll call this scanf numbers. All right, and then I'm going to make a new felony. Let's see. So we need data, and then we need text, and then we need global main, and we'll start putting some code in here. Okay, great. Um, and let's just to recap. Quote. Okay, and let me go ahead and save this before we get too far. So we'll call this this demo1.asm. Okay, so all right, so here's what I think, not last time, but probably last week, and this is really getting annoying, this blanking out thing. I don't know why it does that. Anyway, so I think last week, probably, well, what, we didn't have class Thursday, so it would have been Tuesday last week. We started talking a little bit about scanf, and I think for demonstration's sake, I used %d for an integer. Yeah. Okay. Well, turns out, and I probably spaced on this, d or I for integer right, is a 32-bit thing, not a 64-bit thing. Okay, so which is fine if that's all you want is a 32-bit number, but it could cause problems, and it did in the following way. All right, so we'll do this. Okay, so we've got some strings, and in this case, there's no text, so let's go into our main program, and let's just start setting up. Well, what's the first thing that we've got to have in our program? Right, and then what's the last thing that we've got to have in our program? Right, and then um, so it if memory serves, what it does is it expands the stack before it puts the stuff on it rather than after, um, and which makes sense, right? We need to move the stack pointer before we do stuff. Um, yeah, I'd have to go back into the manual and look it up, but I'm pretty sure that's what the distinction is. Um, okay, so yeah, let's see. All right, so that's just the shell of the program, right? We've stored our link register and our stack pointer to the stack so that we can retrieve them when the program's finished, and we'll return exit status 0 to the program. Okay, so I want to prompt the user for a number. So all this program's going to do is just accept a number as input and then spit it right back out. Okay, nothing fancy. And actually, to demonstrate the issue, let me change that to long int. But I'm not going to change the input one. Okay, so that's a mismatch, but it's a deliberate mismatch. Okay. All right. So the first thing we need to do is prompt the user. So how do we use printf again? What do I need to do? What goes in what registers? Or okay, the address of the format string needs to go into the register 0. Then in this case, that's it because it's not printing any other numbers or something. And so I just need to branch and link to printf. Okay, so that prints, hey, user, do something. All right, then what? I need to accept input from the user. Okay, where is this data going to get put? What needs to go on the stack? So I need to expand the stack pointer by something, right? How much do I need? Well, at minimum, how much do I have to do? 16 bytes, and that's going to be enough, okay? Um, well, actually, you know what? Okay, so I'm going to subtract 16 from the stack pointer. Then what has to go into register 0 to use scanf? Hmm? The format string, okay, but not the string itself, but rather it's wherever it is in memory. So I need to load x0 with np format is just what I decided to call it. Okay, I also need to load something into x1. What's got to go into x1 for scanf? Bueller. Hmm? Where I want to put the data, which in our case is the stack pointer, right? So the scanf is going to write data to memory. Well, I have to tell it where the starting memory address to start writing is. Okay, now that can be theoretically anywhere in memory. Where do we want it for our particular purposes? Well, let's just put it on the stack at the bottom of the stack, so starting at the memory address. It's a stack pointer. All right, so I need to copy the stack pointer over to register 1. And how do I do that? Move like that. Okay, so that's all scanf needs is just two two things to set it up. Format strings address and x0, where you want to put the data, which for our purposes will probably always be on the stack someplace, or in this case at the bottom of the stack. Okay. All right, and then we're ready to branch and link to scanf, and that's Gucci. Okay, so scanf runs. It asks the user for a number. It puts it on the stack. Okay, so where in memory is the stuff, the user's input number? What's the starting address of that data? Whatever the stack pointer is. Okay, how many bytes did scanf just write? Well, what kind of object is a D? It's a 32-bit integer, where I've written it in base 10, so decimal. Okay, so if I've just accepted a 32-bit input and I write that starting at the stack pointer, what memory addresses have I just written to? I've written to stack pointer plus 1, stack pointer plus 2, and stack pointer plus 3, 4 bytes, right? Because the stack pointer was the starting location to where to write stuff, not the only location, right? So where's stuff going to go into memory? Wherever the stack pointer is, let's say that's address 0, let it go to 0, 1, 2, and 3. Those 4 bytes would get written to. Okay, good. Do I write to stack pointer plus 4, 5, 6, or 7 in this case? No, because it was a 32-bit thing. So I only needed 4 bytes to output. Okay, so stack pointer plus 4, 5, 6, and 7 have not been written to by scanf. Does that make sense? Yeah? Okay, so continue A. All right, so I need to get data from scanf. Or sorry, from where is scanf put the data? Yeah, it's at the, well, top or bottom, depending on your perspective, right? But it's at the stack pointer going 4 bits in, right? Okay, so I need to load that data from the stack, right? So how do I load the data from the stack? I need to load a register. Where is the data coming from? Or sorry, which register do I want to stick it in? Okay, yes, I'm going to go ahead and put in register 1, not 0, for reasons that'll become clear in a moment. But whatever, I mean, I'm just sticking it into a register. Where is it in memory? It's in the stack, it's at the stack pointer all the way up through the stack pointer plus 3 bytes. Okay, all right, now, Mr. Harris, why did you choose to put it in register 1 instead of register 0? Good call. Because to set ourselves up for printf, printf needs the format strings address in register 0, and the first thing that it's going to replace, which is in this case a number, in position 1. Okay, so that's why I loaded it into x1 as opposed to x0. Now, that said, if you loaded it into X0 and then you realize later, oh, I needed an X1, you can always move it from X0 to someplace else, right? But if you can think a little bit ahead like this, then you can save yourself an instruction, which isn't that big of a deal, but whatever. Okay, so branch and link to printf, and is that it? Is that all we need? What else do we need? Ah, right. Thank you. Oops. Okay, now are we finished? Prompt the user for stuff, get stuff from the user, load it into the appropriate register, print it, do all the tidying up at the end. I think we're Gucci. Okay? All right, so let's assemble it and see what happens. All right, um, so console. All right, so projects. What did I call it again? scanf numbers and demo. Okay, so we want to do ASMG demo 1.asm output to demo 1.object GCC. All right, this is exactly the issue that he ran into. Why did this happen? I did not enter the number 5454608 blah blah blah, right? Uh, well, that's basically the issue. But let's go in the GNU debugger and see what's happening. All right, so all right, so let's do GDB. All right. Oh yeah. Okay. So I've got to do. Let me rerun it. All right. So what I'm going to do is I'm going to Control C right there. Okay. So let's see. I want to do X for XW stack pointer. Okay, that's not the stack. Let's keep going. I'm not sure that we'll be able to continue with this because I didn't statically. Yeah, okay, let's quit and let's go back and statically link it here. Okay. Oops. All right, so here's what happened. It turns out, and this is what sort of the red herring was. So um, Jack sends me this code and says it doesn't work. It just gets hung, and I'm like, okay, well send me the code. So I compile it, and I compile it, or assemble it. I link it. I do it statically, and it works fine. I'm like, what's the problem, Jack? And he's like, oh, I did not compile static. It's like, okay, fine. But then it's sort of like, well, why should being static or not static matter for whether or not the program works correctly? Now, piping it through GDB and stuff, we've seen that having it statically compiled is convenient, but like the behavior shouldn't be different just because I did or did not statically compile the dang thing. Okay, so what happened was, and it's a little hard to demonstrate here, um, is that when it's not statically compiled for some reason, okay, how much data, so let's look at, once the screen comes back on, what data came out of scanf? It was a 32-bit number, right? But then what did I do right here? I loaded a 64-bit register, okay? So scanf wrote this data here, these 32 bits, because I input the number 5, it input 32 bits, the number 5, okay? But then I proceeded to load in the 64-bit number that goes all the way to the middle there, okay? Now, right here, would it matter? No, because it just so happened that that second um, chunk of 4 bytes was all zeros. But is it guaranteed that it's going to be all zeros? Well, certainly not. And it wasn't in the other case. Okay, so when I ran the program before I statically compiled it, you know why it said 5 billion or 545 billion, blah, 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 blah? Right? What happened was this memory address had a 7F in it, right? This little spot right there. Okay, which means that we had actually loaded in, oops, we had actually loaded in the number 7F, 1, 2, 3, 4, 5, 6. We had actually loaded in that, not just 05. Okay, and does that number look familiar? Oh, looky there. That's the number at output. Okay, so why did this happen? We told scanf to write 32 bits worth of data, but then we read 64. So what do we want to do? We want to either have scanf write 64, or we only want to read 32, one of the two, okay? All right, so back to the code. So you guys see what the issue is? Yeah? All right, now in Jack's case, right, the reason that the program hung is because this was the number for the triangular number that it wanted to compute. So Jack's program was trying to compute the 545 billionth triangular number. Well, that's going to take a while. Yeah. Mm-hmm. Yeah. So if we only loaded in the 32-bit number, it would just load in that, which is what we wanted, right? Because if we've loaded in 64 bits, what it's really loaded in was that, right? So, uh, right, it's just there's a bunch of leading zeros, okay? So, yeah, so either we need to make sure that scanf is correctly taking in and therefore outputting 64 bits worth of data, okay? Or we need to, when we load the data back in from memory, we need to realize, oh, it was only a 32-bit thing and load it as a 32-bit thing, not a 64-bit thing. Okay, so one solution would be the following. Okay, up here in my stack pointer, if I say this, okay, so D or I, right, those are 32-bit things. And then right here, what should I change this to? W1 instead of X1. Okay, so let's run this non-static. Oops, and we'll see. All right, so let's reassemble it. Let's not statically link it because that's where the, okay, and then if I do it correctly, output 6, okay, but it did so because, well, so let's just actually pipe this through GDB. Well, we can't because of the scanning and stuff, but okay. So you guys get the idea, right? So that would be one solution, is to take 32 bits, if we accept 32 bits from the user, realize that and just load 32 bits in and do whatever with it. All right, now, in most of our cases, we're actually writing 64-bit arithmetic, right? We're using all 64 bits for other things. So what happens if you load in a 32-bit thing, but then you want to use it with other 64-bit things? Okay, you can't mix apples and oranges. How do you turn a 32-bit thing into a 64-bit thing? Right, so the number 5 is a 32-bit object and the number 5 is a 64-bit object are not the same thing. What's the difference? Yeah, a bunch more leading zeros, right? Uh, so, but it's 64 bits worth of stuff, most of which are zeros until you get to the lower end. Okay, so one thing you can do is to extend a 32-bit thing to a 64-bit thing, and the instruction to do that is, let me type it here, and it's SXTW. Okay, and there's a bunch of other instructions that are of this form. Okay, the extension things. So basically what this does is it takes a W and sign extends it to an X. Okay, so we start with a 32-bit number 5 and it sign extends to a 64-bit number 5. Okay, now what do I mean by sign extend? So how do I extend 32-bit 5 to 64-bit 5? Just put a crap ton more zeros, right? Okay, so that's easy. But what about if I had -5? How do I sign extend -5 to be in 64 bits? What do I put at the front? Not all zeros, but rather all ones. Okay, so what the signed extend does is it says, okay, if the number I'm dealing with is negative, then I'll sign extend it by padding it with leading ones. If it's not, then I'll pad it with leading zeros and it sorts itself out. Okay, that, by the way, is another one of the really brilliant parts of that using 2's complement. Okay, because what would the number 5 look like in 2's complement 32 bits? Let's just, um, actually, I wonder if the calculator will do this for us. Oh, no, we need to do 5, and then we'll do 2's. Well, maybe not. There we go. Okay. All right, so that's 64-bit version. Okay, but here's what's brilliant about it. What would 32-bit version be? It would just be that. Okay, so to take something that's negative and go from 32 bits to 64 bits, all you got to do is add extra ones on the front instead of zeros. Does that make sense? Is that kind of cool? Hmm? Yeah. I mean, it's 8:30 in the morning, so how cool could it really be? Right? You're hungry. Yeah. Um, yeah. Some of you got coffee. Oh, you need like industrial strength quantities for it to work. Right. After what? Well, okay. See, that's coffee, not caffeine. The two were coffee is merely a vessel. Uh, so he had an ulcer. That's lovely. Yeah. All right. So point being here, right, that doing sorry, to sign extend a negative number, all it's doing is throwing ones on the front. To sign extend a positive or zero, then all it's doing is throwing zeros on the front. Okay, and that's relatively easy to do from a circuit level, as we'll see when we get into the schematic circuity kind of stuff later in the semester. Um, but it's one of the brilliances of doing everything in two's complement is that it makes this trick work, along with a whole lot of other tricks. Okay, so right, 32-bit things are not 64-bit things. So we could, that would be one option, was do sign extension. The other option was realize that we really only loaded 32 bits of stuff in. Okay, what would be the other option? Well, is we just tell scanf we really wanted 64-bit thing. Okay, and then here 64-bit thing. And so when I load from the stack pointer, I really want to load an X. I don't need that. And okay, now we're good. All right, so now let me compile or redo everything. Okay, and now we don't get garbage. Okay, and so why did that happen? Well, we had scanf writing a 64-bit thing. So what memory addresses was it writing to this time? Stack pointer, stack pointer plus 1, 2, 3, 4, 5, 6, and 7. That's 8 bytes worth of stuff, right? And then we promptly loaded in exactly those 8 bytes to X1, and that's good, right? Everything's cool. We don't have the problem. Okay. So this demo, of course, was contrived to demonstrate this problem. Um, in Jack's case, what basically was happening was that the program was trying to compute the 545 billionth triangular number. And how is it doing it? Because how did I ask you guys to write this? I wanted you to use a loop just for the sake of using a loop, right? So what it was doing 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way into 545 billion, blah, blah, blah. Well, that might take a while, right? Because that's a big number. So if we ran it and then like came back next week, maybe it would be finished. Probably not. And actually, what's probably going to happen if you use that large of a number? Well, what happens when you keep adding and you add too much? Yeah, you can get overflow and it could round back, or not round, but come back around on the negative side. Okay, so this was the same problem that Google had with the Gangnam Style video, right? That, excuse me, they were storing the play counts as 32-bit signed integers, which the maximum for that is like 2 point something billion, and then the max negative is negative 2 point whatever billion. Well, and then enough people watched that video that it overflowed, and suddenly the play count was negative, and so they're like, yeah. Um, so they're like, okay, forget it. We'll do 64 bits. Did we talk about that with? Did we ever talk about the Gangnam Style thing in this class? I know I talked about it in 101. Did I mention razor blades in the process? Okay. So how big is 2 to the 64th? Very big, right? So this would be if I had, well, it'd be 7 followed by all F's, right? That's the biggest number, biggest positive number you can express in 64-bit two's complement. That's a really, really big number. Okay, now, what do razor blades have to do with this? So, when I turned 18, I was getting a lot of things in the mail, but what was one thing I got in the mail when I turned 18? Huh? Yeah, I got a free razor from Gillette. It says, Happy 18th birthday, Colin. Here's a free razor. Now, you might ask, how did they know that I was turning 18 and my address? Well, of course, because evil corporations know everything. But what else happens when you turn 18? Yes, gentlemen, we have to register for the draft. So they probably got it from the draft board. All right, anyway, so I get this razor. I shave with it. Not that it looks like I've ever shaved before, but I'm like, wow, this thing is great. Because before that, I was using a double bladed razor, and this was a Mach 3. It had 3 blades, right? Okay, this was pretty nice, right? Pretty Gucci. So a few years later, the Schick Corporation, which is Gillette's biggest competitor, what did they do? They came out with a razor that had 4 blades. They called it the Quattro. And um, not long after that, there was an article on The Onion. So let's find it because it's hilarious. Okay. So the article was this, right? And so this is from 2004, right? Which was not. So the joke is F everything, we're doing 5 blades. Okay. And then a few years later, what did they actually do? Now there's a 5 bladed razor, right? And actually, it's really a 6 blade because there's one on the back to do, you know, which is really handy, like on mustache or, around the bottom of your nose. Hmm? Well, no, it's 5 blades if you just shave sort of regularly, but then on the top end, there's a single blade, which means that you can get like right around under your nose and stuff where you need detail work. Well, we do, right? Okay. It's called an electric razor. Um, anyway, so the reason I mention this is it's kind of like what YouTube did. They said, F everything, we're doing 64 bits for their play counts, right? And it basically for the Gangnam Style or any other video on YouTube to overflow this time, everybody on the planet would each have to watch it several billion, 100 billion times for it to overflow, right? Which is to say, it ain't happening, right? We're more likely to nuke ourselves into oblivion before that happens. I mean, we managed to make it through the 60s, though, so that's, huh? Hey, it's not done yet. So anyway, okay, so let's get rid of chromium. Um, yeah. Okay. So this gets to, in an indirect way, the question. that Lillis had last time, which was I was mentioning how you can get into trouble with scanf, and this actually is a demonstration of that, right? Um, but another way that you could get into scanf is, what about if for some reason the way I had set up my code and done everything, the 8 bits worth of data that I let's say that I had scanf take in a string, okay, and let's say that that string I took in was, I don't know, 64 bits wide, okay. Well, what happened, or let's say that I wanted it to be 64 bits, but the user gave me 128 bits. So that means that scanf has written an extra 64 bits to wherever I've told it to. Well, what happens if by dumb luck there was a machine instruction that the program was supposed to execute at that memory location? Well, if I'm nefarious and I know what architecture the program's running on, and I write some sort of instruction to do something naughty to that memory address, and then the program reads it as if it's an instruction and executes it, then maybe I could do something really nefarious. Um, this is basically buffer overflow kind of thing, right? So Lillis asked a friend of his uh, who does penetration testing, right? Security. No, the look on Porter's face when I said that. That's not what I meant. Uh, okay, sorry. They're doing security testing, trying to break into things that, so this is a good actually job that you could get doing computer security, where, a company might hire you to try to break into its systems, right? And in doing so, they're paying you to do it. So you're going to break in, possibly, and figure out, and then tell them how you broke in so that they can fix it, right? So it'd be kind of like if an art museum hired a art thief to try to steal a painting, and if he actually does it and then walks back into the office and says, "Here you go, I managed to steal it, and here's how," then the art museum could say, "Okay, let's fix whatever it was that you were able to do to get in and steal the painting." Okay. Now, it's criminal activity if they didn't tell you to do this and you steal the painting, right? It's not criminal activity if they ask you to do it. Um, no, that wouldn't work. I think they'd have you arrested, right? Um, well, sometimes yes, but sometimes you end up in federal prison. Uh, you end up in federal prison where there's a different sort of penetration testing. Um, so yeah. Um, okay. So anyway, uh, all of this is to say you got to be careful with your data, right? Make sure that you're taking in and pulling out the correct amount of data, because if you don't, you could run into problems. Now, in the case of Jack's problem, it wasn't really a problem, right? The program was running correctly. It was just going to take billions of computations to get there, right? And so it appeared as if something was wrong, and kind of something was, but it was correctly taking that number and saying, okay, I want to get the 500 and whatever billionth um, triangular number. It's just going to take a while. Okay. All right. So, wanted to talk about a couple of other instructions that. Well, okay. Let me pause. Any questions? Freguntus, Frogin, comments? No. Yeah, Lilith. Uh-huh. Uh, did you statically link it? Yeah. So GDB, and I'm not entirely sure why this is the case, it really does not like to run correctly if you don't statically link things. Well, it'll run, but it gets hung up on printf and scanf. Okay. And so the solution to that for GDB's purpose is just to statically link it. When you execute the program, you don't have to worry about this. But GDB is, there's got to be a solution to that other than statically linking. But yeah, so just do that and it should work. And if it doesn't, then that means there's actually another problem, right? Um, yeah. Okay. Does that make sense? So in practice, you don't want to statically link because it means that, like, I mean, printf and scanf are not exactly really big things, but like, let's just look, for example, right? So if my executable right now is not statically linked, correct? How big is it? It's that many bytes, okay? That's not that big, right? But what about if I statically link it? Now that's quite a bit bigger. Okay, now that's not like horrendous. Okay, 640K, right? By modern standards, that's not that big. Okay, but why is it so much inflated when I statically linked it? Right, it copies all of that stuff in, right? So printf and scanf are programs sitting somewhere, and it's literally made a wholesale copy of it and stuck it as part of my program. Okay, and that's going to take up space. And in this case, you see it took up quite a bit more space. Okay, fine. Um, uh, right. Now, in our case, I mean, is there really that big of a deal to have a 640K program versus a 10K program? No, not really. I mean, this is not a big deal. Um, but that was just loading in printf and scanf, right? What about if we had like some really, really big library that we were using that was part of, like, I don't know, let's say we were writing some database application or something, right? Statically linking could like mega inflate your program. The other thing that where this could cause issues is, um, let's say that we were back in the day. Um, how much RAM does your computer have? Huh? Well, at least one. Well, okay, precisely, right. Today, how much RAM do your computers tend to have? 16, 32 gigs, right? Okay, maybe 8. Depends on when you bought your computer or when you built it, right? But multiple gigabytes worth of RAM. And how much cache is on your processors? Multiple megabytes worth of cache, and then there's usually 3 different levels of it. Okay, so um, even with the 640K, we could fit that whole thing into the fastest version of cache without any issues whatsoever. All right, but let's go way back, right? What's the famous quote about? I mean, I think it's really funny that we ended up with basically 640K. Has anybody heard the Bill Gates quote? 640K ought to be enough for anybody? No? You guys never heard that? Oh, well, all right. Let's consult the bastion of all knowledge of Western civilization. 640K. Oh, did Bill Gates really say it? Huh. Fake news. Okay. So supposedly, 640K ought to be enough for anybody. Maybe he didn't. I guess maybe this is one of those internet urban legends that won't die. Kind of like, did you guys know that Mr. Rogers was a Marine Corps sniper? No, he wasn't actually, but it's one of these legends that won't die on the internet. Um, so yeah, fake news. All right. Anyway, so if we go back, right? So the IBM PC, interesting piece of history, um, could had a max memory that it could support is 640K, right? And um, the machines that were before that, right? So I've mentioned the 6502. The 6502 processor was an 8-bit processor, meaning that its registers were 8-bit wide, but it 16-bit address space. Okay, so that meant that it could address how much is 16 bits worth, by the way? It's 64 kilobytes. Okay, on the nose. Okay, that's not a whole lot, right? And that was the RAM. So the 8-bit Nintendo cartridges, the program on the cartridge started halfway through that memory allocation. So essentially, you had 32 bytes, or sorry, 32K worth of RAM, although not really, because some of it was used for special stuff. And then 32K was allocated to the ROM, the cartridge, where it would read that data. Now, there were ways that, like, some of the fancy games, like, I think, let's see, the old Final Fantasy game. Did anybody play the Final Fantasy? It would have been the three in Japan or one in the US. How many of you guys have played any of the Final Fantasy games at all? No, none of you have PlayStations and have played like, huh? I got your attention there. Away from whatever you're doing, whatever you're texting, you're probably texting a female, aren't you? Yeah, uh-huh. Uh-huh. Mm-hmm. Ooh, well. So we got a love triangle going on, right? Okay. So anyway, but no, I said PlayStation. He's like, hmm? Well, like the original when they were still trying to work with Nintendo PlayStation. Did you guys know that? The history of this? Right. Okay. So what happened back in the day was that Nintendo was going to collaborate with Sony to develop the Nintendo PlayStation. Okay, and it was going to be basically a CD, like a CD-ROM type upgrade for the Super Nintendo. Right. So they were going to collaborate on it. Sony had all the technology to do CD type stuff, and Nintendo obviously had a game console market. So they were collaborating, and I don't know exactly the details, but there got to be some bad blood, and Nintendo decided to back out of it. It was right, and collaborate with try and collaborate with Philips, who also had CD stuff instead. Okay, and Sony was so angered that they said fine, and they went and made their own video game console, and now look what happened. Right? Yeah, it was. Well, there's that, right? But yeah, so that there was some bad blood between Sony and Nintendo. Well, that's how it was even for Sega, right? Like the or the not the US version of the Nintendo stuff, but the Japanese version, so the Famicom and Super Famicom, you could get like extra modules and they would stack on top of each other. So the bottom of the Famicom or Super Famicom had like an expansion port that would connect to the expansion port on another object. So you could have like a hard drive, or there was a disk drive, there was a cassette drive that used like audio tape cassettes. Um, but you could get Famicom games on discs, and there were like actually vending machines where you could take a disc and pop it in and pay a little bit of money, and it would copy a game onto your disc, and you could take it home and play it. And it was cheaper than buying it on a cartridge for obvious reasons. Okay, um, you could get a modem that would connect to a telephone line, and so there were like online systems for the Famicom and Super Famicom. I mean, you could do some really cool stuff, but they were marketing it in Japan as, I mean, yes, you could play games on it, but you could get a keyboard and program in BASIC on your Famicom. They never released any of that for the 8-bit Nintendo here, right? So how did they market it in the US? It was a game console. That was it, right? So all that fun extra stuff for the Japanese market, we didn't get any of that, which sucks. Yeah, I agree, right? But what they were marketing it as in the Japanese market was, I mean, what is Famicom? Family computer, right? So yes, it could play games, but you could also do all kinds of other family type things like programming in BASIC. Because I don't know about you guys, but I have fond memories of a child of me and my father sitting around the computer programming. And it's actually true. I wasn't being facetious, but um, well, yeah, okay, and that's maybe the best way to think about it, right? So Evan just said it's kind of like being a mechanic with dad, right? How many of you guys on Saturday would help your dad change the oil on the car, or get yelled at for getting the wrong wrench, or huh? Do you guys know what I'm talking, or have friends that did, right? Okay, you've seen TV. Yeah, well, okay. I mean, in 30 years, this won't happen because nowadays cars are so complicated that you have to pay a professional to do anything. But yeah, this was kind of for me, the helping my dad with the car thing was helping my dad with the computer. So all of the stuff I know about computing from my childhood, most of it came from that. And then when I got my own computer when I was what, 13 or so, um, then and we had internet access, right? Then I learned a whole lot more. Believe me, the internet was an interesting place in the 90s. So, um, and you didn't have everybody's crazy uncle or grandma on it, which was nice. But um, yeah, okay. So let's get back to what I wanted to talk about. Which, so sorry for that little diversion. Um, so, well, okay. How many you guys probably freaked out on Tuesday because what did you get during the day Tuesday from Canvas? Okay, a shit ton, a metric shit ton perhaps, of new assignments getting created. Okay. And part of it was I was just on a roll. And so I'm like, let me just block out everything for the rest of the semester. And then I'll, kind of pencil things in. So, what are some of the different programs now that we've learned how to do some string processing, right? We've learned how to do byte by byte level manipulation of data. Um, and in our case last time, the example program we wrote was just to calculate the length of the string, of a given string. And we also learned from a security standpoint how to make sure that we don't accept too much data. So we can limit the amount of data that a string that the user can provide. We don't have to do that, by the way, with the number stuff because um, they're going to fit in 32 or 64 bits and that's it, right? So we know that in advance. Um, okay, but if we can do string processing, right, we know the basics of how to read and write to a single byte of memory. Okay, what are the kinds of things that you guys used that dealt with strings when you were in 111 or maybe 211? Okay, so two upper and two lower. What else? String to int and int to string. Well, that would be floating point, but yes. Okay, because a double is 64-bit float, right? We haven't talked about floating point stuff, although we certainly will, right? That's going to be an important thing. And there'll be an assignment that goes with floating point. I'm going to blow your minds with the coolest algorithm ever. The fast inverse square root thing. Yeah. So, okay. Anyway, when I show you how that algorithm works, you guys are going to be like full on the GIF of the guy with the like exploding head. Well, like the yeah, you know what I'm talking about, right? Okay. So uh, what other things did you guys use in 111 and 211 that did? So these would be Java functions, built-in things that did string operations for you. You definitely used the length. We just wrote that. All right, two upper, two lower, int to string and string to int. What else? Hmm. Okay. What used strings? What other things could you use? The string copying. Okay. So what would a comparison mean in that case? Like which one's longer or mm, okay. Substrings. Yeah. So then, so that would be like a lot of your searching type algorithms or sorting or things of that sort, right? So, or determining like if you've got two strings, is one of them a substring of the other? So, like John and Jonathan. Okay, good example. Okay, so all of those sorts of things are things that, um, are built-in single commands in C or Java, and you just type them, and then bam, that's it, right? No problem. Well, but how do they really work? You guys can't see the smirk on my face, but that's the next sort of chunk of assignments. Okay, so what did I post for you guys? The first little chunk, right? So I did string copying first. You'll see why I did that. Okay. Then what's after that? Two upper or two lower? Okay. I don't care which one you guys do. Either just pick one. Do either two upper or two lower. It's basically the same trick either way. Um, I thought about having you guys do like have the user type in U or L and then do the correct thing accordingly, but basically you'd be writing the same code twice, and I thought that was kind of pointless. So just pick one, either two upper or two lower. I don't care, and do that. Yes. Yeah. It it everything either goes to two upper or two lower. Um, yeah, right. Because Java, Linux, C, those are all case sensitive. Okay. And so if you don't care about case, then and you're working on a case sensitive system, then what's really happening is everything's getting piped through two upper or two lower, one of the two, right? Which I mean, it doesn't really matter which one you pick at that point, but you have to, like, from an operating system standpoint. So, like, let's take DOS for example. DOS was not case sensitive. Uh, and so if you typed a command in lowercase versus uppercase, I think it exactly the same things would happen. Okay. Um, and so how would that then be working? Well, it would just be taking the input and piping it all through either two upper or two lower. I think in its case, it was probably two upper because uh, you normally typed everything in uppercase in DOS. So, um, but like if you typed little c or big C colon, right? Well, you guys never, how many, you guys probably never used DOS, did you? Oh man, children, you have no idea. Um, you guys have no idea. All right, so uh, so yeah, the first assignment with the string level stuff is just to copy a string, right? And I chose an arbitrary, I think I chose 31 characters, which would mean 32 bytes, just basically completely arbitrarily, right? Because what really is going to be happening, you're going to be doing it on a byte by byte basis, and so it's going to be a loop. It doesn't really how many times you do the loop, but so I just picked 32 as a round number um, for uh, for for coding purposes. Um, so you guys, I think, will see why I did string copying before I did two upper or two lower. Okay. How is two upper or two lower going to work? So mathematically, what's the trick? Well, yeah, or 2 0 because it's hex, right? So what was capital A in ASCII? It was ASCII 4-1. Okay, what's lowercase a in ASCII? ASCII 6-1, right? So the difference between those is 2-0. So if I want to go from upper to lower, what do I do to each ASCII thing? I just have to add the number 2-0 hex, right? That's pretty easy to do. And if I want to go from lower to upper, what do I do instead? Subtract 2-0. So same deal. This is why I'm only going to have you guys write it one way, because it's sort of the same trick from one case to the other. It's just whether or not you're adding or subtracting. Okay, but here's the thing. If I have so if I type a string and I have a digit in there, right? So like, let's say I type Wabash 1832 or something, right? Should two upper or two lower do anything to the 1, 8, 3, or 2? No, because there's no such thing as an uppercase 1 versus a lowercase 1, right? They're the same thing. Okay, so what that means is that when you read in a byte, meaning an ASCII character, you're going to have to determine, is it in the range of the alphabet numerically, or is it something else? And if it's in the range alphabetically, you know it's a letter, and you know it can then modify it. If it's not, you don't modify it. Okay, so there'll be a nice conditional stuff going on there, of course, right? Um, and the other restriction I'm going to make just for simplicity is, so if we look at an ASCII table, um, so originally ASCII was 7 bits, but it very quickly was extended to an 8th bit, and that got you another um, 64 bits. Okay, or sorry, another 128 characters. So extended ASCII got you um, a bunch of these letters. So like, I know it's a little hard to see on the screen here, but this character right here is a capital C that has the little dangly bit that we use in French. It's called the cedilla, right? So that's the difference between soft C and hard C. Um, or those of you who speak Spanish, uh, you've got here 164 and 165. What's there? Yeah, Enya. Okay, so the N with the tilde, which is the Y sound instead of the N sound. And that's important, right? Because there are words in Spanish where if you forget the tilde, well, what's the difference between años and anos? Rather big difference. Okay, huh? Do you know what they both mean? You can guess. Años is year. Anos is yes, something else. Okay. Um, all right. So you guys, for the two upper and two lower, don't have to worry about the extended ASCII characters because, for example, the a true two upper function would be able to turn lowercase Enya into uppercase Enya, or lowercase c with cedilla to uppercase c with cedilla. Okay, but there, notice that the upper and lower cases aren't a constant number off of each other in the extended segment. It's only in the regular segment that they're kind of in order like that. Okay, so don't worry about the extended ASCII characters that are letters. Just do it for the standard 26 A through Z from English. Okay. All right. Well, once you do two upper and two lower, whichever, then there's string to int and int to string. One of those is slightly easier than the other, but they're both going to require a little bit of mathematical trickery. And in particular, have you guys in Java, did you ever use the mod, or this might have been the percent operator, right? So where you do division with remainder. Okay. We'll talk about how you do division with remainder or integer multiplication and division. We'll talk about that, well, sometime next week. Okay, so next week we need to talk about, well, one, I'm going to see if we can find a space where you guys could bring your pies and we can do like a bit of a coding workshop. Two, we need to talk about some of these mathematical things like whatnot. We need to talk about recursion. That'll probably take a day. And then at some point we'll start talking about floating point. Yeah, okay, so that's where we're going. I'll let you guys know, because if we're going to do a coding workshop, obviously it won't be here in the classroom. So let me find a place where we can do that, and we'll go from there. Yep.
Hey, I got an announcement for everybody. So, I don't know if you know, TechPoint is